thank you so much for having me, and I'm going to be talking to you about the links between spatial cognition and numerical cognition and some of the possible threads that ties them together. So for today's topic, I'm going to tell you a little bit about myself, my background, then a general overview of spatial and numerical cognition and that possible underlying thread that they have in common, some of my graduate work on spatial reasoning and the factors that may affect it, and my current postdoctoral research in preschool and school-age children on numerical cognition and relational concepts, and then some of the future directions that we have in mind. Okay, so I'm a postdoctoral researcher in the Cognition and Learning Center, as Jenny just said. I was born in Miami to Cuban immigrants. I grew up in Miami. I went to Miami-Dade College from 2008 to 2010. I graduated from their honors program, and then I transferred to Smith College in Massachusetts, in Northampton, where I earned my BA in psychology in 2012. This was the first time that I'd ever been away from home, from my family, and as the first in my family to go to college, that was a really new and exciting territory for me. It was a big transition. I couldn't wait to leave home and have that traditional college experience because that's not very common in Miami. We live at home for a really long time. We go to Florida International University or Miami-Dade College, and we kind of just stick around, and we don't tend to leave for college. But my parents, on the other hand, of course, had a really hard time with my leaving. But eventually, so I went to Smith, and I got a little bit homesick, so I ended up, after graduating, moving back home, and I started my program in psychology at FIU. As Jenny already said, specialized in developmental science. My research broadly focused on spatial and associative learning and memory in preschool children. So I like to think about development from a relational developmental systems perspective, where development of cognitive skills emerges from the complex coacting relationships among multiple interdependent systems that create both inter- and intra-individual differences in developmental trajectories and outcomes that we see. According to this theory, human development is really complex, it's dynamic, and it requires active participation on the part of the organism. So for example, humans are not passive recipients of their environment. They explore, interact with, and often change their surroundings, and these human-environment interactions influence cognitive development, according to this view. So these systems include psychological systems, things like abstract concepts, symbolic systems like language and numbers, ways of mentally representing the world and visualizing your environment, which is very useful when you're trying to navigate. So they also include cultural systems. So these are our societal structures, social context, cultural upbringing, education, and essentially all that is the nurture part of nature versus nurture. And of course, they include biological systems, right? Being able-bodied, your physical development, your brain development, hormones, physiology, genetics. This is the nature part of the nature versus nurture. So these systems together can enhance or hinder cognitive and physical development. They coact and influence each other over time to result in individual and group differences in cognition. And by examining all of them, we can get a fuller sense of what causes the developmental outcomes and behavior. So for my graduate research, I was interested in the development of spatial cognition specifically, and I conducted several studies that each considered one or more of these systems as a predictor of children's learning and memory skills, including the links between hippocampal-dependent associative learning, otherwise known as trace island conditioning, or EBC, and spatial reorientation strategies. So we proposed that this specific EBC paradigm could serve as an indirect proxy for hippocampal function in young children, and how it might give us insights into the relationships between the hippocampus and spatial reorientation performance in young children who might not be able to give us reliable functional MRI data. So we published a review paper on the topic in Frontiers in Psychology, and that became my master's thesis project, in which I found that EBC performance was tied to children's abilities to use geometric cues, but not landmark cues, during a spatial reorientation task. And then these findings were then published in the journal Developmental Science, and I also did structural MRI work, and we didn't find anything with spatial reorientation and hippocampal volume, but we did find some stuff with EBC and hippocampal neurite density, and we're working to publish that, those findings. They're actually under review right now, the European Journal of Neuroscience. So I also examined the relations between childhood wayfinding experience and navigational strategies and anxiety in adulthood. That was something I was really interested in, was, let's go way back to childhood and see what kinds of experiences could influence your later spatial abilities. And this paper was published in the journal Cognitive Research Principles and Implications. And for this study, we asked undergraduates about how far they'd been allowed to travel and how often they were allowed to go outside between the ages of 6 and 15 years of age. This we called childhood wayfinding experience. We also asked them about their current anxiety levels around navigating, which we called wayfinding anxiety, and also their wayfinding strategies. That is, whether they use an orientation strategy or a route strategy to navigate. So an orientation strategy would be using global cues like the sun, aerial maps, cardinal directions, and a route strategy would be using local cues like landmarks and egocentric cues like your body's left and right turns. So here we found that greater distance traveled in childhood was associated with less reliance on a route strategy, which is known to be less efficient than using an orientation strategy. And it was associated, so that greater distance traveled was also associated with less anxiety about having to navigate unfamiliar territories, which makes sense. We also found sex differences in childhood wayfinding experience, wayfinding anxiety, and wayfinding strategies, where men reported greater childhood experience playing outdoors and traveling farther distances, less wayfinding anxiety in adulthood, and less use of a route strategy in adulthood than women, and using more of an orientation strategy, which again is what we would expect. So I also examined, for my dissertation, the links between spatial and relational language comprehension and spatial reorientation strategies in early childhood. And this paper is one of my dissertation studies, which I will be sharing with you today, since it's the most relevant to the work that I'm doing right now in Jenny's lab. And it's relevant to relational and numerical concepts in children. So I'm currently working on editing, formatting, and submitting it to the Journal of Cognition and Development. So my graduate research was based on the idea that spatial memory abilities are neither fixed nor the result of one determinant, such as brain development or experience. So psychological, cultural, and biological systems work together over time to result in these individual and group differences in spatial abilities. So this approach to development can extend to my current research on numerical cognition and relational concepts in early childhood, where arguably all these factors come together to create behavioral outcomes in number knowledge. And so the idea here is that by thinking about development holistically and examining the multitude of factors that may be related to the development of cognitive abilities, researchers can comprehend not only typical trajectories, but also how social and biological factors intersect to create the differences that we see in these abilities. So hence, this is why we need more interdisciplinary studies. Okay, so now to get into it. A large focus of my dissertation was spatial cognition. So I want to start by defining it and discussing the different types of spatial abilities. So spatial cognition is this type of intellect that helps us understand our three-dimensional environment and the objects within it. It's characterized by a variety of adaptive, malleable skills that are necessary for the survival of many species, especially mobile and visual animals such as humans. It also develops and improves with age and experience. So spatial cognition is really important for navigating the space around us and for manipulating the objects within it. It allows us to construct spatial abstractions in the forms of maps, graphs, and even analogies. So for example, comparing ideas for the purpose of clarifying and explaining. So there are two broad types of spatial cognition. They're often studied in the literature with distinct neural bases. We have between object representations and transformations. These are your large-scale spatial abilities. Sometimes they're referred to as extrinsic object encoding, or rather require extrinsic object encoding. So this is when you compare objects and features in the environment to other objects and features or to yourself. It's useful for navigating, remembering the locations of objects, and it relies heavily on the hippocampal brain region. And then you have within object representations and transformations. These are small-scale spatial abilities, which are ways of representing objects in relation to themselves, but from a different vantage point. Sometimes this is referred to as intrinsic object encoding. It involves understanding the internal structure of an object and relating parts of that object to itself. So sometimes this is also referred to as mental rotation. It's useful for species that engage in tool making and tool use and relies mainly on the posterior parietal cortex of the brain. And so both of these spatial domains have a genetic component and also develop and improve considerably during early childhood. And although they rely on different neural systems and comprise different cognitive and behavioral skills, they also tend to be very positively correlated with one another with respect to performance. So if you're really good at navigating, then you're probably also really good at mental rotation. So for my dissertation project and my master's thesis, I was interested in the neural basis and behaviors that are pertinent to large-scale spatial abilities like navigation and reorientation. So spatial reorientation is this subcomponent of spatial navigation where when you're navigating, sometimes you get lost and you have to reestablish your sense of direction after you're disoriented. So when animals get lost in the environment, they have to regain their sense of direction in order to find their way around, to locate objects, to find food, rejoin their conspecifics, so other members of their species. So again, really useful for navigating. It's a large-scale spatial skill. And there are a few mechanisms for spatial reorientation, and among them are geometric cues and landmark cues. So geometric cues denote the shape of an environment in terms of the relative positions of points, lines, and angles. So you kind of figure, oh, this is more or less a rectangular space, for example. You use the walls. There's two short walls. There's two long walls. You figure, like, this is a rectangular room. Landmark cues include salient features in the environment like buildings, street signs, light fixtures, and these tend to be less stable than geometric cues, right? Because a stop sign can change, a building can be taken down, or a new building can be built. So spatial reorientation is found to be malleable. It develops with age, experience, verbal skills, and the environmental layouts. So for example, we see developmental changes in spatial reorientation abilities between the ages of 4 and 6 years, where older children will be able to combine multiple cues, so the geometric and the landmark cues of the room, to locate places like hiding spots after being disoriented, whereas younger children will tend to fixate on the geometry of the space and they ignore larger cues or more salient cues like landmarks. And some researchers argue that this is because of the existence of a geometric module in the form of hippocampus that processes exclusively geometric cues and is impenetrable to landmark cues until children learn spatial words like left and right around the age of 6 years of age, or 5 to 6 years of age. But we also see, interestingly, individual differences where some 4-year-olds perform better than some 6-year-olds on the task. So we often use language to help us describe, represent, and understand the space around us, which of course helps us to navigate it better. So we might use words like near or below or big. So this object is really big, this object is small, this object looks like this object is closer to me, is farther to me, farther from me. So we use language to refer to exact locations, things like the duck is behind the fence, the dog is in front of the house, and we may talk about how something is related or connected to something else in the environment using systems of spatial localization called frames of reference. So we have different kinds of frames of reference. So we have intrinsic and relative frames of reference that are body-centered ways of understanding where we are and where we're going. So if you say like walk straight ahead, turn left, spin around, come back, walk back. So those are intrinsic and relative frames of reference. So someone is in front of the house or they're behind the house because the house would have an intrinsic front and a back. Someone is to the left of the house, the right of the house, and that's going to depend on who's left and who's right. And then we have our absolute frames of reference that include stable information that is outside of and independent of the body, salient features like the sun, cardinal directions like north, south, east, and west that don't change whether you're facing one way or another. So I focused on intrinsic and relative frames of ways of talking about space because they develop earlier than absolute frames of reference and are easier for young children to understand. So we see that there is variability in language that is linked to cross-cultural differences in navigation strategies and maybe linked to spatial aptitude. So for example, people whose languages don't contain words for left and right will often use and rely on absolute frames of reference like cardinal directions to navigate. They're a lot better at it. We also see that women in those cultures tend to use more of an orientation strategy and be more efficient at navigating than women in cultures where, like in the United States, for example, where we do use left and right a lot to refer to directions and to give directions and follow directions. So experimental, correlational, and cross-cultural research suggests that there is a possible causal link between language and spatial cognition, where having more rich spatial language facilitates better spatial cognition. So one argument for why language is so important for the development of spatial abilities posits that having this richer grasp of relational language in general would translate to paying more attention to the spatial world and your environment, the objects within it, and the relationships between objects and between yourself and objects, and then thus better performance, leading to better performance on spatial tasks. So on the other hand, some scholars argue that it is knowledge of specific task-relevant words rather than just having more spatial language in general that predicts or at least correlates with performance on these spatial tasks. And my dissertation study examined both of these possibilities. So I wanted to know, does more relational language or does specific language foster spatial skills? So while previous studies have found a positive associations between language and spatial cognition, there still remains a paucity of data on the relationships between children's knowledge of relational language and their large-scale spatial skills in particular. So some of these studies have looked at spatial language and also spatial language that parents use, and smaller spatial skills like smaller scale spatial skills like mental rotation abilities. So we don't know too much about children and large-scale spatial skills and how that relates to spatial and relational language. So while accounting for age and other smaller-scale spatial skills and general cognitive abilities, because we know that large-scale and small-scale spatial skills are correlated. So when we talk about relational concepts, we're not just talking about spatial elements. So relational concepts, which is what I was interested in looking at as it relates to numerosity and numeracy skills. So relational concepts are words that describe spatial temporal connections between objects or between yourself and other objects. Words like across, like that chair is across from me, below, near, around, left, beginning, first. These are known as where and when words. Also, relational concepts include words that describe features, size, and quantities of objects. So big, tall, few, round, rectangular, sort of like what and how many words. They're the words that denote how many we have, so quantity, and what about an object, like what does an object look like. So how do numbers relate to relational concepts? So spatial and numerical cognition are closely linked. Numbers are relative and spatial in nature. They have a size, they have an order, they have a location, they can be compared with other numbers. And for example, all of the words that you see here describe relational concepts, specifically spatial concepts. Although a child might look at the number 10 and say it's bigger than the number 5, or that 1 is less than 3, they would be describing quantitative concepts, right? So we have some things are spatial, where it's just telling you about the location of a number. So this number comes first, this number comes last, this number is above this number. This number is to the left of this number, but you can also talk about it as, well, this number, number 10, is bigger than the number 6. So as children learn about the relative nature of numbers, they begin to draw analogies between numerosity, so the oneness of a number, the two-ness, like what does it mean to have 2, what does it mean to have 1, what does it mean to have 3, and corresponding symbolic numerical representations, like 1, 2, 3, 4. So these are your Arabic numerals. And so based on previous research, there might be a relation between types of relational concepts and numerical abilities in children. So this is what I would predict, that there would be some kind of some link between not just relational concepts in general, but certain types of relational concepts and certain numerical abilities in children. So specifically, children's understanding of relational concepts would predict the growth of their numeracy skills, such as how number words are spatially oriented and related to each other on a number line. So that's what I would predict. So for my dissertation, so now I'm going to get into my dissertation study. I was interested in how spatial reorientation related to the hippocampus and hippocampal dependent learning and memory, such as eye blink conditioning. Of course, biology is only one predictor of spatial cognition. So because language is relevant to the ways that we think and talk about the world, I wanted to measure early understanding of words that describe relations between the self and objects in space to see if children's understanding of the so-called relational language contributes to their spatial reorientation performance and the types of strategies that they would rely on to reorient themselves toward the correct locations. So based on relational developmental systems theory, one of my dissertation studies focused on these psychological and conceptual predictors of spatial cognition. So broadly, I was interested in how children might incorporate relational language into their reorientation strategies. The overall objective of the study was to investigate individual differences in children's knowledge of basic relational terms and more specific directional words, like left and right, in relation to their choices on a spatial reorientation test. So my first aim was to explore children's knowledge of directional words, like left and right, in relation to their spatial reorientation strategies. And I predicted that children's understanding of these directional terms would be positively associated with their increased ability to choose the correct corner on a spatial reorientation test. My other aim was to then explore children's knowledge of just basic relational terms, near, around, in front of, in relation to their spatial reorientation strategies. And I thought that, again, whether it was specific or general, it was possible that children's understanding of just general relational knowledge would still be associated with their increased ability to choose the correct corner on a spatial reorientation test. So that would be their use of landmarks, right? So if they're choosing the correct corner, they're relying on the landmark to help them decide. So for this study, 39 children between 4 and 6 years of age participated in 5 tasks. A 15-minute spatial reorientation test, a 1-minute assessment of their knowledge of left and right, 10-minute Boehm preschool test of basic concepts, a 5-minute processing speed task, and a 10-minute mental rotation test. So for the spatial reorientation test, the setup here was similar to that used by Learmonth and colleagues in 2008. Children were brought into a room with 3 white walls and 1 red cue wall and stood within the small enclosure, which had 1 box in each corner. The experimenter, that was me, would place a small toy in one of the boxes closest to the cue wall while the child was looking. And then the child was blindfolded, spun around many times, like 20 to 25 times. It was a really hard task to administer. They were spun around a bunch of times until they were almost falling over and I would have to catch them. And then the blindfold would be removed and they were asked to point to the box that they thought contained the toy. So they did this for 8 trials. And I also had them, before taking off the blindfold, I would ask them, can you point to the location of the door to make sure that they were disoriented? And if they couldn't tell me what the door was, I figured, okay, you're disoriented enough. So, and in case you're wondering, so the inner barrier, because I've had a lot of people ask me this, the inner barrier was used to confine children's movement to a smaller range. This has been shown to increase the difficulty of the task across species, and so this would add to the individual variability and reduce the potential for ceiling effects in children's performance, which we were trying to avoid. And since we were interested in individual differences, we didn't want the task to be too easy.
Vanessa? This is a quick question. That internal barrier,
yeah.
Is it perfectly square? Or is it rectangular?
No, it wasn't square, sorry. It was 4 by 6, yeah. It was 8 by 11, I think was the big one, which is kind of standard, and then it was 4 by 6. Yeah, 4 by 6 feet. Yeah, and then 8 by 11 feet, yes. And that was my advisor's son. That's the perks of having advisors with kids. They lend you their kids for all their studies. Okay, so we had two dependent measures of interest. So we had, so here it says the dimension. So 8 feet by 11 feet, and then 6 feet by 4 feet. And then it was 18 inches high. And I was the one who cut the fabric. I was the one who cut the PVC pipe. Like, it was a nightmare, but. And then we had to have the fabric in the ceiling to make sure that they couldn't use the lighting cues or any ceiling cues. All right, so we measured children's ability to combine the salient cue with the geometry of the space by evaluating their correct corner responses. This is their combined strategy. So if they are relying on the landmark cue, they would probably, if they were ignoring geometry and only the landmark, they might be going to either this corner or this corner, maybe roughly equally. If they were combining geometry, if they understood this is a rectangular space, so if my toy is here, then if I turn around, this would be the spot, but the cue is here. So if the cue is linked to the hiding spot, I know it has to be there. So that was the idea there. So they're combining these cues to be able to locate to lead them to the right spot, the correct location. And then we also measured their ability to encode the geometry or the rectangular shape of the space by assessing how often they gravitated toward the correct or diagonal, the correct or the diagonal corner of the room when making the choice, right? So if they were completely ignoring the landmark, they would be like, oh, if this is a rectangle, it's like, well, it's here. If I'm standing over here facing the short wall, it's like, okay, it was hidden over here. So even if they don't understand left and right, they kind of know, like, okay, it's somewhere in this vicinity. But if they're turned around and everything looks the same, they're like, oh, it has to be over here. So that's why they would gravitate toward those two. And we did get most kids, very few kids went to this corner or this corner. So like the far correct corner and near correct corner. We had very few. So that was good. That means that the room was rectangular, and they were able to encode that. Okay, so for our general relational language assessment, we administered the Bowen test of basic concepts. This is designed to assess preschoolers' understanding of basic relational terms, concepts like spatial concepts, so locations, quantitative concepts, it's numbers, size, quantity, temporal concepts, so time, words denoting time, like a word like finished, like so-and-so is finished, or so-and-so is starting a task or beginning a task. And then other types of words that didn't fall neatly into those categories, so like different and same, all. So there were 52 items on this task. These kids were 4 to 6 years old, so we administered 52 of the items, just asking about relationships between objects and people. So here we have an example. So they would be shown this picture and say, point to the dog that is nearest to the tree. And so the dependent measure here was the correct, the percent correct items that they got correct, percent items that they got correct. And then for left and right, we gave them a really quick left-right assessment where I had the child face away from me so that I wouldn't give them any cues unknowingly. And I asked them, can you please raise your right hand? Okay, can you please raise your left hand? And then I did this in alternating. So right, left, right, right, left. And it was just simple, here, raise your hand. Okay, cool, put it down and raise your left hand, so on and so forth. So we looked at just the percent they got correct, and then also their the first 2 trials of whether they knew right and left the first time they were asked. And then we administered a processing speed control task. So this is part of the NIH Toolbox Cognitive Battery. So it was the pattern comparison processing speed test. This is a quick 90-second task that's administered via an iPad. Just measures the speed of processing information. Basically, children were shown pairs of images and asked to respond as quickly as possible to whether or not the items are alike. So depending on their age, it could be yes or no on the screen, or a happy face and a sad face. And if they're different, they would click on the sad face. If they're the same, they would click on the happy face, and they're supposed to do this really fast. And then the dependent measure was the number of items identified correctly in 90 seconds. And this processing speed test served as our control for kind of general cognitive abilities, to make sure that anything that we found just wasn't because they're just smart or something, or really just have good general cognitive abilities, or can process information quickly, but that was specific to the BOEM and how it relates to the spatial reorientation. The BOEM and the language assessments and how they relate to spatial cognition. And then we also administered this small scale spatial test, and so we can control for it. The children's mental transformation task. This is a 32 item task that measures mental rotation abilities. Children were asked to point to one of the 4 shapes that the 2 broken pieces make up. So which of these do those pieces make up when put together? And then their dependent measure is just the percent correct. And this served as our small-scale spatial control to make sure that any effects that we found were related to spatial reorientation skills and not mental rotation skills, since they are correlated. Right, so again, AIM 1 explored children's knowledge of directional terms, left and right specifically, in relation to their spatial reorientation performance, and AIM 2 assessed whether children's knowledge of general, basic relational words would relate to their spatial reorientation strategies. So as per my specific aims, I predicted that children's understanding of relational words, whether specific or general, would be associated with their increased ability to choose the correct corner on the spatial reorientation test. So bivariate Pearson's correlation analyses revealed that scores on the left-right assessment were so examined in AIM 1, did not actually relate to correct corner choices on the spatial reorientation test, but only scores on the BOEM-3, so the BOEM test of just general relational concepts, positively correlated with correct responses on the spatial reorientation test. So nothing with left-right, unfortunately, but just general relational language, we did find a positive correlation. However, because I was interested in individual differences, I ran multiple linear regression analyses and found that when controlling for age, mental rotation scores, and processing speed, children's scores on the left-right assessment that was examined in AIM-1 were significantly positively associated with their geometry use as opposed to their correct responses on the spatial reorientation test. So this is here percent correct plus diagonal corner, that would be their use of geometry, and then just the correct corner alone would be signal their use of the landmark. However, the scores on the BOEM-3 assessed in AIM-2 were unfortunately not related to any spatial reorientation strategies when controlling for age, mental rotation, and processing speed. So maybe they're just getting better at both because they're both very highly correlated with age. So in other words, children with higher scores on the left-right assessment, it's AIM-1, but not higher scores on the BOEM-3, that's AIM-2, chose the correct and the diagonal corners most often on the spatial reorientation task, independent of age and performance on other cognitive tasks. Okay, so just to summarize, the objective here was to investigate individual differences in children's knowledge of specific directional words, it's AIM-1, and more general relational terms, that was AIM-2, in relation to their choices on a spatial reorientation test. So one surprising finding was that even though distinguishing between left and right wasn't associated with positive performance on the spatial reorientation task, as I would have predicted, I found that when accounting for age and other cognitive abilities, children's knowledge of left and right was associated with reorienting by geometric cues or the shape of the environment. So in accordance with AIM-2, there was a positive correlation between performance on the BOEM-3, which tested children's comprehension of just general relational concepts, and spatial reorientation performance, or how well they did on the task. But this effect was diminished when controlling for age, mental rotation skills, and processing speed, which just leads me to believe that age is really the thing that was tying it all together, that they're getting really good at these tasks with age, as we would expect. So these findings could offer some insights into the associations between understanding relative frames of reference and the strategies that young children rely on to find their bearings, suggesting that psychological constructs like language may influence spatial cognition in early childhood. Of course, this was a correlational study, so that's important to keep in mind. Parents, however, might want to use more spatial language with their children during playtime, maybe teaching them the difference between left and right at earlier ages, since the language that children hear from their caregivers when participating in spatial activities has a positive effect on language production and spatial achievements. And also, including spatial language as one of several factors that affect the development of spatial reasoning offers us a richer understanding of human spatial cognition. Okay, so now having said all that, so for my postdoc studies, I was really interested in the links between space and number, so having examined the relations between relational language and spatial reorientation, I was also interested in maybe how this relates to numerical cognition. So since numbers appear to be spatially oriented in our minds, the way that we think about them, right? Like 1 is over here, then 2, then 3, then 4. So numbers have this kind of spatial location and orientation in our minds. So I wanted to investigate whether conceptual knowledge of the spatial environment and understanding relations between objects can contribute to understanding relations between numbers, or vice versa. So which one is driving which? Is it understanding numbers that helps you understand spatial or general relations among things in the environment, or is it that understanding the relationships between things in the environment helps you understand the relative nature of numbers? And so I wanted to kind of understand which kinds of concepts, so spatial versus quantitative, would relate to which types of numerical skills. So number ordering type of skills, or just comparing numbers. The skills that allow you to compare numbers and understand differences in size and quantity. And what implications might this have for early math and vocabulary education? If we start teaching children about spatial and numerical relations in preschool and even in daycare, could this have some kind of educational implication for later math learning? Okay, so the project's main purpose these longitudinal studies aim to disentangle the association between understanding different types of relational concepts and the various numeracy skills in preschool and kindergarten age children. So my questions were, what types of words may help children solve which types of numerical problems? Or do number skills help children think about relations between items? So is it, what's the directionality here? Relational concepts predicting out to numerical skills, or numerical skills predicting out to later relational concept skills? Okay, so first we conducted a pilot study to understand the associations between knowing numbers and relational concepts in preschool children, so at this very rudimentary level. So the aim of this pilot study was just to establish an association between just understanding quantities and relational concepts in preschool children. So we decided to test preschool children on their basic number knowledge and comprehension of general and relational concepts to see if the associations between numeracy and different types of relational concepts could be found early on at a more rudimentary level with something like basic counting. And here I predicted that there would be a positive correlation between number knowledge and understanding relational concepts, specifically the spatial and quantitative aspects of the BOEM, of the test of relational concepts. So for the pilot study, we have 23 preschool and daycare children that we recruited from Rutgers preschool and daycare centers. The mean age was about 4, ranging from 2 years to more than 5.5 years of age. We administered 2 15-minute tasks, a give a number test and a BOEM 3 test of relational concepts, which I also did for my dissertation. So for the test of relational concepts, what we did was we combined items from 2 tests of relational concepts. So the latter task is actually it's a spatial language assessment. So we looked at items that were repeated on both. So we had the BOEM we administered 38 items from the BOEM, and then because each item, it's 76 items, and each concept is tested twice. So we administered 38 items for this pilot study. So the concept tested once, and then we added some spatial language words that were not on the BOEM. So 5 extra words. So they were given 43 items in total. It was about 15 minutes. And then for the number task, we gave them the give a number task. This is where the child is asked to give the numbers 1 through 5 and 10. So 4 blocks of 6 numbers. So they're asked in random order to, we show them a puppet and we say, this is George, like this is Curious George, like he's throwing a party for all his friends and he wants, it's gonna be a banana party. Now George needs 1 banana for the party. Can you give George 1 banana? And so the child would take the banana from the bucket, put it onto the plate, we say thank you, and we take it, we move it aside, and we keep asking them for different numbers. Can you give us 3? Can you give us 5? Can you give us 10? To see if they really understand quantities. So what we found was that preschoolers' number comprehension was positively correlated with understanding relational concepts. So yay, like that was what we would predict. So the scores on the BOEM, so how many relational concepts they understood, were positively related to the overall scores on the given number task, which measured whether they understood numerical quantities. It was pretty strong correlation. And then it also was interested in their understanding of spatial and quantitative concepts. So we broke it down and we looked at their scores on the different types of the different concepts, so whether they understood specific types of relational concepts. And we found that preschoolers' number comprehension was positively correlated with spatial and quantitative concepts. So the correlation actually, interestingly, between spatial concepts and numerical knowledge was a little bit stronger, but they're both pretty strong correlations. There are also more spatial words on the task, to be fair. There's about 25 spatial words assessed and I think 13 quantitative words assessed. So that might be why. Okay, so we find, so for our conclusion, we find that preschool children who understood more relational concepts, especially the spatial and the quantitative concepts, also understood more numerical quantities. So we know that there's a positive relation between numerical knowledge and knowledge of relational concepts, but I wanted to know, does this effect hold for more advanced numeracy skills? Do number skills predict relational concept knowledge or vice versa? Which one is driving which? I wanted to know this with, understand this with a little bit more advanced numerical skills. So for the next study, we asked, do types of relational concepts correlate with types of numerical skills in proficient counters? And if so, what is the directionality of this association? So the aim of study 2, broad aim, was to characterize the link and directionality between types of relational concepts and types of numeracy skills in proficient counters. So we asked, we wanted to investigate the link between relational concepts and numeracy skills in kindergarten-age children, and we predicted that children's general knowledge of relational concepts would predict their later numeracy skills in school-age children, controlling for general vocabulary knowledge at the onset of the study. And so our other aim was to investigate the direction of the link between types of relational concepts, so like spatial, quantitative, temporal, other, and different numeracy skills like number ordering, number comparison skills, number line estimation skills in kindergarten-age children, while controlling for general vocabulary at the onset. And I predicted that children's knowledge of spatial and quantitative concepts would predict their later number ordering and number comparison skills respectively. But it could also go the other way around as well. So it was a little bit exploratory. We thought it could go either way. So I thought, okay, spatial concepts are going to be more related to the ability to order numbers, to put numbers into their proper order, whereas quantitative concepts would be more related to their ability to compare numbers and compare the size and quantity of numbers. So for this study, this was a collaboration with Dr. Jenny Chan at the Education University of Hong Kong. So study 2 recruited 104 kindergarten students who were 5 to 6 years of age from 11 classrooms across 4 public schools in 3 school districts in Minnesota. So the study was conducted at the University of Minnesota Twin Cities before 2021. The children, their mean age was almost 6 years old, so it ranged from 5 1/4 to about 6.5 years of age. They were given 4 tasks at 2 time points, 6 weeks apart, so 3 numerical tests and 1 test of basic concepts. And they were administered also 1 general vocabulary control test at time 1. So for the test of relational concepts, they were given the BOEM, but for older children, so the one that I administered was for preschoolers, they were given the BOEM for school-age children. So just a sample from the BOEM, a child is asked to point to the dog that's nearest to the bowl. There were 50 items. It was about a 10 to 15 minute task. And so for the verbal number tasks, They were asked to compare numbers, so the number comparison task, they were asked which number means more, and then they were given 2 values. They were also asked to order numbers, so the examiner asked children to rearrange Arabic numerals from smallest to largest, and then they were also asked to estimate numbers on a number line. So they were shown a number line with the endpoints, so 0 to 20 or 0 to 100, and they were given a target number, and they were told to put it where they thought it went on the number line. And then they also were given a general vocabulary test. So this was part of the Kaufman Brief Intelligence Test. It's the vocabulary subtest. It's the control task to assess general vocabulary abilities, 60 items, measuring receptive and expressive vocabulary. So the child would be asked to point to images of things like clock, money, dishes, illuminate, and it took about 15 to 30 minutes, depending on the child's age and ability. So for these analyses, I ran a series of cross-legged panel models to assess the bidirectional relationships between the specific types of relational concepts and the numeracy skills controlling for general vocabulary at time 1. So this is just kind of like our basic model here. So you would have relational concepts given at time 1, numerical skills, number relation skills given at time 1, and then at time 2, and everything's predicting out to time 2. And we wanted to know if maybe these relational concepts here would predict the number skills at time 2, or if the number skills would predict the relational concepts at time 2. And we did expect for the relational concepts to predict relational concepts at time 2, and the number skills at time 1 to predict the number skills at time 2. So again, we wanted to investigate the link between general relational concepts and each numeracy skill in kindergarten age children. So when we ran here, we looked at relational concepts in general, looking at different number skills, so the number comparison, the number ordering, and the number line estimation skills. And we find here that number ordering skills at time 1, this pathway here, predicted relational concept knowledge at time 2, controlling for general vocabulary and relational concept measures at time 1. And then we also found that the relational concepts and number ordering skills at time 1 predicted relational concepts and number ordering skills at time 2. That was expected. That wasn't what we found interesting, but we did find that here number skills, number ordering specifically, was relevant to what was predicting later relational concepts, which is really cool. And then we wanted to look at specific relational concepts. So we want to investigate the direction of the link between types of relational concepts, so spatial and quantitative concepts especially, and different numeracy skills, number ordering, number comparison, number line estimation in kindergarten age children. And we found that, again here, number ordering skills at time 1 predicted spatial concept knowledge at time 2, controlling for general vocabulary and spatial concept measures at time, or sub-scores at time 1. So also really interesting, and it goes with our prediction. So I thought number ordering was relevant to understanding spatial concepts. So it makes sense that these would be related. And then of course you have the what we would expect, spatial concepts predicting spatial concepts at time 2, and then number ordering at time 1 predicting number ordering at time 2. And then we looked at number line estimation, and we found that number line estimation was pretty strongly predictive of spatial concepts at time 2. It's negative, but it's actually positive. It's actually related. So better performance on this task, the number line estimation task, was associated with better performance on the spatial concept task because it's about the precision on the task. So that's why there's a negative relationship there. So it doesn't mean like better performance on number line estimation was equal to worse performance on spatial concepts. So this was also pretty interesting that we also found that being able to put a target on a number line and being really close to that target, to where it's supposed to be, that was also relevant to understanding spatial concepts, which I would predict that as well. And then also interestingly, we found that quantitative concepts, their knowledge of quantitative concepts at time 1 predicted their number comparison skills at time 2, controlling for general vocabulary and spatial concept measures at time 1. So also interestingly, so I thought that quantitative concepts would be more relevant to comparing numbers, right? Because it's about like, well, the value of these numbers. So is this bigger than this, smaller than this? So yeah, so that makes also perfect sense. And then, okay, so those were our good models. So we ran a bunch of them, but those were the ones that had a good model fit. So our data fit our models really well. And so what can we conclude here? Okay, so children's numerical skills, both basic counting skills and more advanced numeracy skills, are associated with their understanding of relational concepts. But by elementary school, numeracy skills, so number ordering and number line estimation, specifically predict later understanding of spatial concepts, while understanding quantitative concepts predicts later performance on a number comparison task specifically, which is in line with what we would predict theoretically. So the findings suggest that there is a possible bidirectional relationship between knowledge of numbers and that of relational concepts. And for the future directions, we want to continue doing this with preschool children. The idea is to run the same models, but with preschool children. So we want to continue to recruit and repeatedly assess them on their counting abilities and their knowledge of relational concepts. So we want to administer, or we've already started doing this, but administer this a vocabulary test. So the Peabody Picture Vocabulary Test has over 200 items that measures receptive vocabulary. They're shown 4 images and asked to point to the image that represents the particular vocabulary word, like eating, cake, fire. And we'd administer it at session 1, and it would take about 15 to 30 minutes, depending on the child's age and ability. Okay. Okay, I think I'm good. I was talking fast there at the end because okay, thank you to everyone. I would like to thank my postdoc advisor, Jenny Wong, director of the Cognition and Learning Center. She's wonderful. She teaches me a lot of things. She believes in me. Thank you so much. My research assistants, our lab manager at the Calc Lab. And then from grad school, I like to thank the Florida Education Fund. They funded me. I had won the McKnight Doctoral Fellowship, funded my doctoral stipend and my tuition and all of that in grad school. The graduate seed funds, so these are these internal grants that we got in grad school to do our research, and then the University Graduate School Dissertation Year Fellowship that helped me finish writing my dissertation. My late graduate advisor, Dr. Bethany Reeves Sutherland, director of the Brain and Behavioral Development Lab. Unfortunately, she passed away of breast cancer when I was writing my dissertation, and it was a very sad story. I like to thank her. And then my co-graduate mentor who took me on, who's actually her best friend, the director of the project on Language and Spatial Development Lab at FIU. So, and thank you to Rutgers, of course, for having me. Tired. Okay.
We have time for some questions.
Okay, we have time.
So I just have some general question.
Yes.
For your study 2A2, which you did here, you collaborate with another lab.
Another Jenny,
So,
yes.
So was the language the same, or is it cost close? I was just trying to understand if the tasks were the same. Was it English and the expectation of ideas about numbers?
Yes.
Was the same?
Well, not the number task, the number, so our preschool study is different. We're not administering the same thing, so that was a study with kindergartners. Ours is with preschool and daycare children. But the Bowen test was very similar to what I administer with the preschool children. It's just that it's a little bit more advanced for older children. It has
But
some,
the study too, you said before, was someone who was in an overseas institution, or is it?
Oh no, yeah. She moved. So,
Okay, so it's basically the population is the same. There's English-speaking children.
yes,
Oh,
English speaking.
okay.
Yes. Yeah, in the United States, yes, it
And the
was.
second question is, you talk about experience and how numbers changes. like, did you look at birth order, right? So maybe if the child is an only child
Mhm.
versus a sibling pair, maybe their knowledge of kind of like the words are different.
Yeah.
Based on just exposure.
Yeah, well, there might be something to that with language and birth order. Maybe somebody who studies language might know a little bit more about this. Maybe like only children or older children tend to be a little bit better with their vocabulary skills are a little more advanced because they spend more time talking to adults rather than talking to children, to other siblings maybe, and hanging out with other siblings. So there might be some relationship with the skills of children who are born first versus born later might differ there. I'm not sure about numbers though, so if someone has something to say about that, I don't know if birth order matters with respect to understanding numeracy. Yes.
I mean, first, just a follow-up. So like these are all daycare kids, right?
For the first study, yes,
Okay,
they're
so
daycare and preschool children. Yes.
So that might get rid of some of the birth order effects
Yeah.
if they're all
Yeah.
interacting with a lot of kids.
Yes.
The second thing I was going to say, you may have handled this with the intelligence test or something like that, but I was wondering if there was things that were not well correlated that were both maturational kind of things. So like if there's some kind of, you did check vocabulary size or something like that, I think.
Yeah.
But it's
General.
always possible that there's, because you're saying there's a spatial and numbers are related together, something that's maturational but not well correlated with that would help make a stronger link between these and not just say, well, they're better at space, they're better at number, they're better at everything. Do you know what I'm saying?
I'm not sure.
You're saying that their spatial ability, as they develop spatial abilities, they get better number
Yeah,
abilities,
yeah.
and better number abilities gets better spatial. But if
Yeah.
they're just getting better at everything,
Yeah.
the
Right.
fact that they're getting
Yes.
these are correlated doesn't mean anything because it's
Right,
correlated
right.
with everything.
Yes. Yes, so that's why for my dissertation I did try to control for like different types of cognitive abilities. So we did we had the mental rotation test that we controlled for. We had the processing speed test. I had for my thesis I looked at episodic memory as well. For this we only have controlled for general vocabulary knowledge because general vocabulary knowledge could be related to, if they're really good, if they just know a lot of words, then that could be, that could confound the findings, the relationships between relational language and number. So that might be correlated with the amount of relational language that they understand or the relational concepts that they understand. So that's why we focused on controlling for general vocabulary abilities. But yeah, we haven't we haven't looked at other controls. Really focused on vocabulary.
Let me follow up on that. So one question that one might ask is like, why don't you control for all these things for these kids in
As kids, you can't get them.
Yeah.
So these are preschool children, and
Yes.
and we're trying to do a longitudinal design.
Yeah.
Which means that we want to go back and test them over and over again. Which means that we can only give them so many things.
Yeah.
Because they're gonna run away.
That's another
We
thing
give them
too.
my things to do. So that's a great constraint on the kind of research that Vanessa is doing, and unfortunately,
Yeah.
we're not quite able to do all that, but
Yeah.
we're making steps.
Yeah. That's the thing with young children. It's like giving them too many tasks. I had that issue with my dissertation. Where it's like, do we cut it in half? I was somehow able to get the kids in the MRI machine and to do all the behavioral tests in one session, but it took a long time. We'd take a lot of breaks. It was really difficult. But that's a really good point. Yeah, there's a lot of things that. Yeah. Mm-hmm.
Just two questions. On your number line estimation tests, is your number line on linear scale or log scale?
That was done by another researcher, but I think it was, so they only had endpoints. Let me just pull it up here. So they had, sorry.
I think Paul might be
Sorry.
asking whether the error is calculated from linear or log.
No, it's just, I mean,
Right.
since you're measuring on
Yeah.
how close they were to
Yeah.
writing, I just want to know,
Yeah.
is the scale linear?
Yeah.
Or is it on log rates? Because there's reason to think that the inner number line is on log scale.
mhm.
So I just want to know, are you
Yeah.
measuring for correctness of position
Yeah.
on
Yeah.
linear or log scale?
Well,
Yeah,
how big was
I'm
the
not-
scale?
Yeah.
How high does it go
Sorry.
for a task like this?
Yeah. So So I'm not 100% sure how the number line actually looked. I just found this on Google, but basically they just put the endpoints, and it was either they did it with 0 and 20 at the endpoints, and then from 0 to 100, and all they had was a line. And I'm not sure if the two lines from 0 to 20 or 0 to 100 were the same length, or they were shown at the same time, but they just had the endpoints, and then they were asked.
Is the middle number
Yeah.
on the, so if it was 0 to 100,
Yeah.
is 50 in the middle?
Yeah, so I would imagine that 50 would be in the middle, but I'm not 100% sure. No, I don't know.
Yeah,
Yeah.
these are, so that's the next step we're planning to do. So these are researchers that just took the task from Bob Sigler and just gave it to kids. And I don't think Bob Sigler is a strong believer in log scale necessarily. And so one of the tasks that we have is to potentially reanalyze this data to see whether we can figure out more about their MMO estimation. But what Vanessa was showing here is just whatever measures that they already
Yeah,
posted.
so they were already scored, and I did.
The other question was, so you mentioned a number of times a measure of knowledge of relational concepts. Am I right that the measure is understanding of what's counting as a relational word?
Yeah. So like, what does this word mean? Like, what is, So the concept would be the spatial, concept would be, is it spatial, is it quantitative, is it temporal, is it, but then like the words for that are specific spatial locations, quantities and sizes, words that denote time, words that denote other things, like just comparing like how big is, how different is this from this other thing, or is this smaller than this?
So the correlation you're getting is between whether or not they've put the phonology together with the right concept.
So,
and so
so did they understand the word, and then what does that word mean? Is it a spatial, is it a locational word, is it a quantitative?
and the measure of whether a word counts as relational is?
Oh, yeah, so the connections between the different items in the environment. So like it could be like what and like when, like what word, like spatial locational words, like where words, how many words, so words that denote how many, words that denote time, and then other types of words. So how they're connected in those ways, like by locations, like the relative locations, the relative size and quantity, in terms of time, like something happening, first or finish. This person finished this task. That's a time word. There weren't too many time words, and then the other types of words that don't fall into any of those categories. Yes.
A question about the dissertation study. So you found that success in picking the exact right corner, so the corner that is, say, to the left and right helps to get that one, and closest to the right wall, it did correlate with the performance on the Boehm test, but it also correlated with age, and if you control for age, that wipes out the Boehm effect.
Yeah.
So I'm guessing that performance on the Boehm test and age co-vary.
So age, the Boehm was highly correlated with age.
So
yes.
you suggested, and I mean, the issue then is we can't tell if it's really getting better in relational terms or just getting older. Do you have any thoughts on follow-ups that you might be able to run that could help disentangle those, where you can see, is it just getting older, is it just maturity or development in some other domain, or if it really is the relational language knowledge?
Yeah. That's a really good point. So I'm gonna have to probably throw age into the mix there and control for age as well. So we were thinking vocabulary was gonna be the thing that was gonna affect the findings. So we have to control for general vocabulary knowledge, but I haven't added age in there. So we're gonna that's something that's important to think about as well.
So maybe in the future it'd be possible to have enough kiddies who are in the same age band to where age is taken care of.
Yes.
I wonder if we could cycle back around to, so the correlations you find are that numerical reasoning positively correlates with spatial reasoning. What was the theory for that? Like, why do we expect that to be true?
So that numbers and space. So because like the way that we think about numbers is kind of in spatial terms. Like one comes before this, like one comes before two, comes before. So we think about it kind of on a like in our minds, kind of from left to right, kind of on a number line. We relate numbers to each other. We say like they have a relative size and order. All of these things that are relational concepts.
So is the causal story the other way around then? That spatial reasoning is what gets you better number cognition?
So we thought, so a lot of the previous studies, they consider it as being relational concepts, kind of driving later number knowledge and understanding just the relationships between things is going to help you understand numbers and get better at early math skills and early number skills. But so that's kind of what I thought, but we thought it is possible that number skills could then drive your understanding. Understanding of numbers could drive your understanding of the relationships and the connections between things in the environment. So we looked at, that's why we did the cross-lagged panel model stuff, and we actually did find that it was actually numbers, number ordering, that and number line estimation that predicted out to relational and spatial concepts, but then that quantitative concepts predicted out to number comparison skills later on. So that kind of would lead me to believe like there could be just some bidirectional thing happening, because we kind of found both.
Yes, just a follow-up question on that. Sorry. Quick follow-up question, clarification. So it's not that great. If you looked at the particular, because you had a pretty big bucket of relational terms. If you looked at whether there were certain relational terms that were predicted by the number knowledge more so than others. So you had spatial relations as well as temporal relations. Is it the case that one or the other is differentially affected by the earlier success of the number?
Yeah, so we don't, unfortunately, there aren't enough temporal or other type of words to really like look at that to get a lot of variability in that. So there was, I think, for the preschool task, there was one word that denotes time, and then there were like 4 words that denoted other types of words. It was like missing, like point to the clown that's missing a hat, for example, would be like an other type of word that doesn't really quite fall into spatial or quantitative. Although missing, I guess you could think about it as missing a 0, so I don't know, maybe you can always like reason it out, but there were others like all, like point to all the apples or something like that, like different, same. So, and then this is actually pre-coded on the Bowen manual. They actually already have that list, that's kind of listed out. But there weren't a lot of other types of words and that to look at, but when it did, the strongest relationships that I found were with spatial and quantitative words, yeah.
Oh, I was just wondering if you could help me remember about the left-right stuff from your dissertation, because I definitely remember your nice, like, it doesn't make any difference flat line, but then what did you control for that made it so, was it age again? Yeah? Yeah. So I think this is kind of a little bit what Paul was talking about a little bit, but to me it makes total sense that you wouldn't find a relationship with left-right assessment.
Yeah.
Because you actually said while you're doing the presentation, like just because they don't know this is left, this is right, they still are kind of like, well, it's this side.
Well, that's I think that's the theory there. So like, so there's the whole idea with the hippocampus and the geometric module that it's kind of impervious to like other types of information in the environment. So it's you're able to process the geometry of the space when you're really little, or like in other animals, they also find that they're like really good with geometry and like not great with landmarks. But then like children start understanding left and right, and all of a sudden it's like, oh, this cue is to the right or to the left. Or that's the idea, but you can use left and right with geometry as well.
Exactly. So I guess what I'm kind of confused about is why we would think that knowing what sounds are associated with this half of things, right, is predictive of anything that's different from understanding I have this half and I have this half, right?
So even in language,
right?
Necessarily.
To me, it makes sense that there wouldn't be any of that going on, because I guess, and I know this is controversial, but I don't think that you have to have a label for something to have a concept of.
Right.
Right. So I know it's controversial.
That's actually, it is controversial. Actually, not everybody. Not everybody believes.
It's not controversial for.
Yes, it's true. I'm aware, but I really think that. So
no, that actually, that makes sense. I mean, tend to be a believer of like language influencing thought, but I know that that's like there's the Whorfian, anti-Whorfian hypotheses, but you really don't, because even very young, I mean they've done spatial reorientation tests with 18-month-olds and then very very little kids, like, and it's very, but then there have been studies on verbal shadowing and like how they block your ability to use language, and they find that you're not able to do it, but then at the same time, if there's verbal shadowing going on where you have to talk while doing a task or something so that you can't think, you're really distracted. So I'm not sure if that's necessarily an indicator of whether language is or isn't used or is a factor in your performance on spatial reorientation tests. But it's pretty controversial to think about.
I guess what I was actually going to
language.
ask is whether or not you have an idea of how we could actually tap into whether the kid has a concept of that without being like raise your right hand, raise your left hand.
Right.
Right. Anyway, but because I feel like
I
that I would
yeah.
understand how that would matter, but I don't really understand why that would matter.
Yeah. Yeah, I was kind of going for, some researchers that have looked at left and right, there's been a little bit of work, not too much work on it, so I was kind of trying to see if I could replicate maybe some of that work, or like maybe the little kid, if the 4-year-olds maybe understood left and right, maybe that was maybe helping them perform better on the task, but apparently not, so it doesn't seem to be the case there, but so maybe language isn't as strong as, because there is a way to, so you can have a concept, the idea is you can have a concept of space without thinking without labeling anything, just kind of in a visual sense.
Yeah. But then the label can increase the salience or help with remembering that relation, the stability of the
For sure, and actually your bone thing, where, because,
Yeah.
it's like I can nearest that, I don't know, that makes a lot of sense. Anyway, sorry.
That's one thing we tend to see over and over again is that insofar as language affects thought, it almost always affects memory retrieval, memory encoding factor. But I want to get back to the causation story.
Poor Ryan, sorry.
Which I'm still thinking about. Because I feel like that's what this is about, right? Like, we want to know why they're good at these things and why they relate to each other.
Yeah.
And so I'm thinking about the number stuff. This is interesting about the spatial. So it seems like they just naturally build spatial encoding representations for spatially encoded representations of numbers. Like doesn't necessarily, the causal story is not spatial reasoning causes the number thing, but the number thing just is spatially encoded.
Yeah.
And
So it's intertwined. They're inextricably linked or something.
So a student shared a paper with me recently. When they were describing it, I thought it sounds impossible, so I had to read the paper. And it was about very, very little babies. They were like six months to a year or something. And they would present them sequences of numbers auditorily in the language that they're exposed to and a language they've never heard. And babies have a preference for stable ordering, even if they don't understand what's being said.
Yeah.
So like in Japanese, they still
Makes
prefer
sense.
it if the numbers go in some kind of fixed order, even though they don't know what they mean.
Yeah.
And I'm like, okay. So it seems like
Makes
that
sense.
is that's
Yeah.
a natural thing that little babies have, is they want the numbers to be ordered in a stable way. And
I'm aware that we're like going over time here. I want to clarify that for that study, that particular study that inspired a lot of my work in my grad school and here and continuing, they actually found that 15-month-olds failed to recognize the stable order in language counting. So it's not like you don't need any prior experience to recognize the stable order in your native language counting, because obviously you have to learn the counting in your native language. What I think is crazy is all those research, I think they may even have gotten newborns to associate larger quantities to right.
So I've been reading stuff on that too. And even insects have this.
And even insects, right?
Even insects have
They're
this.
showing in insects and in other species like.
So that seems to be a totally innate thing that you have unless you learn how to read right to left. And then it's a race.
And that's, again, a super controversial topic.
Yeah.
Right.
People argue like what's really going on.
Right.
But I've been wondering lately if like children have this stable ordering preference as like a downstream effect of the fact that language itself is temporally ordered. Because that seems like the first step is language is, like at least we can produce it, right? It has to be words in a particular order. And so maybe children are biased to think sequentially.
Yeah.
And then the spatial encoding for numbers comes out of that and then it feeds into spatial stuff. I don't know.
Yeah.
But I'm speculating about this. I have been thinking about this lately.
It's
It's interesting.
an extremely interesting,
Yeah.
empirical question. I just wish that we could just get babies.
Yeah. Yeah. If parents just let us like have their babies.
Just go to the hospital and get it in the operating room. You know?
Yeah.
I'm still like shocked that they were able to do those imitation studies on newborns. Like they just went into no.
I've heard so much.
You're talking about the Milsoft stuff?
Yeah.
I have heard from someone that really the only one that does it is sort of like the smile thing. The other ones, he happened to get 1 or 2 examples.
Oh.
So it's not a reliable thing at all.
Yeah.
And fun fact,
Yeah.
the same researcher that did the counting study did a huge scale replication of the Milsoft study and failed to find it. It's the same researcher. She's called Virginia Slaughter. She might be one of the greatest persons in the field. Anyways.
Failed to replicate the imitation.
Yeah, the newborn imitation.
Like the 3 emotional
Yeah.
faces.
Yeah. Yeah.
It's
Or like the
just
sticking
fun
out, the one they stick out their tongue and then
Yeah. The fun fact is the same person.
It's funny though because I don't know if you ever tried this with your daughter, but when my cousin's baby was really, really, really little, like my aunt and uncle would do that with her, and she would stick out her tongue, like, "Oh my gosh, she's imitating," and I'm like, I don't know, man. It seems pretty convincing. It seems like it's a real thing, right? But I don't know.
It's a good candidate for confirmation bias though, because
Yeah.
when they get it, then
Yeah.
you remember.
Yeah, that's true.
Don't get it like that.
Yeah.
If I email you, will you send me these slides?
Yes.
Cool.
And thank you for everybody's feedback.
Thank you.